Is there anybody in the waiting room? I noticed nobody's really, the participant list has not really increased since I've been here. Oh, there we go. Okay. Everybody's coming in now. Okay.
I was I was sharing the screen and didn't notice that. Yeah.
Okay. Sorry, I was getting nervous that nobody was here. Okay. Hi, everybody. We're just cutting it a little bit close, but it's all good. Welcome to part 3 of Atmosphere, Ocean, Climate Dynamics. Let's see, is Mira here? Our first speaker? I don't think so.
So for the posters, we just flipped the first and second, if that's,
Yeah.
but I mean, it's a bit harder with orals, right? Because people
Well, I
might,
was going to ask actually Adam and Mark. So there's it looks like there's a 10-minute gap in the middle of this session.
yeah.
So we do have a little bit of a buffer to start a couple minutes late, but
Yeah, I think that 10-minute gap is meant to be so poster presenters can give, unless do we actually have,
we
no,
don't
we don't have a poster presenter for this.
we don't have a scheduled poster presenter.
Right,
Oh, I think
right.
our first speaker is no, our first speaker is still not here. Okay. Mira, are you here? I'm a little reluctant to flip the order just in case somebody's planning to come in 15 minutes to hear the second talk.
I tend to agree with that.
Yeah.
No, for sure. It works for posters, but I think
Yeah.
orals is
Okay.
worth it.
We don't even have questions to ask because we haven't heard any talks today yet. I did try to wear a more colorful shirt today. Spirit of the session.
Yeah, sorry, gone gray.
Yeah. Okay, well, everybody, welcome. Hope you can stick around, and we'll see if our first speaker shows up a couple minutes late. Manny, you're here. You're a third speaker. Did you want to just do a quick screen sharing check? Make sure everything's good?
Yes, hi.
Hi.
That would sound good. Let me
Great.
try.
Sure. Take advantage of this extra couple minutes.
Are you able to see my screen?
Yes, I see. I think I see the wallpaper. I don't see a
Yes.
presentation.
Okay.
Oh, there we go. Yeah.
Is it full screen?
Yep. It's all good. Yeah.
Good. Okay.
Okay. Thank you.
No problem. I'll stop sharing it.
I guess I can email the speaker. I have their address. Okay, we've got a lot more, a bunch of more people joining now. Mira, are you here? Don't see you. Okay. Yeah, for those of you who just joined, we're just waiting for our first speaker. So we have a few extra minutes, but please stick around.
Judeline Jean-Baptiste, voilà.
Oh, Robert, can you elaborate on that? I did notice that the different parts of the session have different Zoom links. Clicked on 50/50. Okay. Well, it's not 50/50. Well, that's weird. Maybe our speaker's in a different room then. Okay, well, this is not climatic data rescue in Canada. So we're in Atmosphere Ocean Climate Dynamics Part 3. Pass that information on to the organizers, and hopefully they can fix that.
Maintenant, il a fallu que je paye sur Wi-Fi pour celui-là. Il a fallu que je paye sur Wi-Fi pour entendre autre chose. Hein? Ben, j'entends du bruit, oui, j'entends des gens parler, mais je ne sais pas, je dis, mais pourquoi il a fallu que je paye sur Wi-Fi? Tu sais, c'est pas comme tantôt. Tantôt, c'est apparu d'un seul coup, hein? Il n'y a pas eu de problème. Puis là, j'ai ça, Michel Belland. Puis là, j'ai tout ça, désactiver le son. Mais pourquoi je désavais? Démarrer la vidéo. Ben, on peut bien démarrer.
C'est pour qu'il te voit.
See, organizer, maybe want to mute. Mute. I'm not I don't have the Zoom powers here, but
Yeah.
we could just
Michel,
whoever.
Michel, your audio's on. You're not muted.
Oh, sorry.
Okay, thank you.
Désactiver, so.
I can mute all, but I have to identify the person speaking to mute.
Okay, thank you. Okay, all right, and then we have one more time for those of you who are just joining. So this is part 3 of Atmosphere Ocean Climate Dynamics, but unfortunately we don't have our first speaker yet, so we're just waiting for either a late showing or we'll continue with our second speaker in about 6 or 7 minutes. Okay, well, I think we're not going to have our first speaker. So it's 9 minutes after the hour. So Kyle, do you maybe want to go ahead and share your screens, and then we'll get ready to kind of stay right on schedule. You can start in a minute.
Sure thing.
Thank you. Okay, so we can just wait a minute in case there's any late arrivals. Okay, well, I guess we can get started. So yeah, welcome everybody to part 3 of Atmosphere Ocean Climate Dynamics. And after that slow start, thanks for your patience. Our first talk of the session is by Kyle Hablum, who's going to talk to us about variability of biomass burning. So go ahead, Kyle. Thanks.
Hey, hello everyone. Thank you for tuning into my talk. In a moment, I will be discussing how the consideration of the variability of biomass burning emissions can be an important factor towards our simulated climate. But first, I would like to acknowledge my graduate advisor, Hansi Singh, as well as our collaborators on this project, Phil Rash, Patricia Durip-Tigny, as well as Haruki Hirasawa. So I'll start with some motivating background for our work. So recently, work done by Durip-Tigny and colleagues had noticed that in the CMIP6 contributions of CSM2 in the historical simulations, that towards the end of the historical period, there was this anomalously fast decline in Arctic sea ice. This was in contrast to a much smoother, much slower decline within the CMIP5 contributions from CSM1. And what they were able to do was attribute this rapid decline in Arctic sea ice to the way that biomass burning emissions were treated within CMIP6. So if we look at the emissions here on the right, we can see that there's this rapid step change in the variability towards the late historical period. And this large variability was the result of the use of satellite observations driving those emissions. Prior to this, it was mainly fire proxy measurements that were relied on to develop these emission files, which resulted in much lower variability. And then going into the future, in the future SSP projections, simply smooth, almost zero internal or interannual variability was used. And what they show was that it was actually this increase in variability that led to this rapid decline in Arctic sea ice. So to further explain this, Durip-Tigny et al., as well as another study done by John Fasulo this year and his colleagues, show that along with this increase in biomass burning variability is also a cloud thinning effect. So we can see this really strongly within the cloud droplet number concentration, particularly in this mid to high latitude Northern Hemispheric region. Along with this was an increase in the amount of shortwave radiation that was absorbed at the surface, as well as an increase of surface temperatures and a fairly large increase at that. So following on this, we were able to show that this increase in surface temperature as a result of considering a high variability in the biomass burning emissions led to an amplification of the hydrologic cycle within CSM2. And namely, we saw fairly large increases in evaporation, the amount of water vapor in the atmosphere, as well as the precipitation. And again, we really saw this largest increase in the Northern Hemisphere mid to high latitudes. So from these three studies, we can see that this variability seems to be important when deciding the state of the climate, particularly within CSM2. But a question that still remains is how much of this is driven by changes in the forcing when we start to consider this variability in the aerosols. So to tackle this question, we designed and ran a set of idealized simulations to be able to start to pinpoint what might be going on here. So we used, again, CSM2. We ran this under constant 2000s climatological input conditions. We also fixed the sea surface temperatures as well as sea ice concentrations. And this allowed us to directly quantify the radiative forcing by removing the bulk of the feedbacks. So we ran 3 different emission scenarios of the biomass burning emissions. The first was a fixed baseline where we subjected the model to a constant annual monthly mean cycle. We then simulated the high variability period within those CMOS-6 biomass burning emissions and just repeated those. And we also ran an idealized variability scenario where we purely isolated the temporal variability that we see within the high variability of CMOS-6. So one of the things that these simulations allowed us to do is to directly calculate the radiative forcing change within those CMOS-6 emissions, or particularly that high variability period of the CMOS-6 emissions. So if we look at the difference in forcing when considering 0 interannual variability versus the variability used within the CMOS-6 emissions files, we can see a fairly large positive change in that radiative forcing. So if we're looking globally, it's on the order of about 0.1 watts per meter squared. But as expected, we can see that it's highly concentrated in that northern hemispheric mid to high latitude range. So particularly over 50 to 70 north, we actually see increases in the radiative forcing as large as on the order of 1 watt per meter squared in the annual mean. So we can see that the radiative forcing is affected by the variability in biomass burning emissions, at least in CSM2. But a large question that still remains is what the underlying mechanism behind this is. It's a little odd that if we were to see the total amount of emissions integrated over time stay the same, that purely the temporal timing of these emissions can have such a large effect. So we use our idealized emissions scenario where we're isolating the temporal variability to start to dig into this a little further. So we're able to, using these idealized scenarios, reproduce a lot of the previous findings. So we see this cloud thinning effect, particularly in the cloud droplet number concentration or reductions in that. We also see a reduction in the liquid water path, indicative of a reduction in clouds. And this is particularly strong, again, over the high impact region in the northern mid to high latitudes. And these both act in concert to increase our cloud radiative effect, which is effectively saying that difference in clouds between these two scenarios result in more shortwave reaching the surface. And then if we zoom in on these high impact regions and consider their evolution over time, what we can see is that there are 2 very different regimes. So firstly, we can see this regime associated with the low emission years. And then conversely, we can see a second regime that is associated with the high emission years in these idealized scenarios. And something that we see when comparing these 2 is that there's really a bias towards these low emission years as seen here. And what this is starting to hint at is a possible nonlinearity in these cloud variables to differing amounts of aerosol emissions. So to dive into this a little further, what we did was simulated these fixed baseline emissions at varying emission amounts. And what this allowed us to do was see the smooth response to both the cloud droplet number concentration and the liquid water path to varying concentrations of aerosols in the atmosphere. And what we find is this strong nonlinear response in both of these variables. This was, as expected, based upon the work of Karslow et al. In 2013. And what this nonlinearity is really telling us is that these high emission years should be resulting in less of a unit change in these cloud variables than the low emission years. That the low emission years kind of win out on their radiative effects. And what these result in is a nonlinear response in the forcing. And then something else that we can see is really important along this nonlinear curve is where we sit along that. Where along this curve are we fluctuating and changing? We have this strong nonlinearity at low aerosol burdens, and then it becomes a little more linear towards more polluted atmospheres. So if we overlay the variability within the CMOS emissions, we can see that we're in this strong nonlinear region, that deviations around this baseline really, or their radiative effect will really depend on whether it's deviating up or down along this curve. We can then take this one step further and look at fully coupled runs within CSM2. So here I'm showing the CSM2 large ensemble, 50 members from that see this high variability period. And we can directly see this nonlinearity within the large ensemble as well, really indicating that this is a strong effect and explaining some of the effects that were previously seen by some of the studies I talked about earlier. So I'll finish off with a few takeaway points. Firstly, considering the variability in aerosol emissions may have a large impact to the overall aerosol forcing. We find that increases in this variability of biomass burning emissions acts to reduce the total negative forcing of aerosols. Increases in this biomass burning variability and effectively this reduction in the total negative forcing acts to warm the surface and amplify the hydrologic cycle. This is particularly strong in the northern hemisphere of mid to high latitudes. And we see this change in the aerosol forcing due to the variability because of a nonlinear cloud response. I should also note a really important caveat of this work is that so far these simulations that allow us to see this nonlinearity and start to tease apart what may be going on have only been done in CSM2, which is known to be one of the more sensitive models to aerosol cloud interactions. So it is entirely possible that either CSM2 is overestimating this result or this result may be diminished in other models. So thank you very much for your time, and I'm happy to take any questions.
Great, thank you, Kyle. Yeah, I forgot to mention it before, so if you have any questions, you're welcome to type them in the chat. We have time for a couple questions. You can also just unmute your mic and ask if you want. Okay, well, maybe while people are thinking about questions, I'll ask just a quick one. So your idealized emissions, like can you say more about how you chose, like why are you doing spikes and not something sinusoidal, or I don't know, how did you choose the shape?
Of course, yeah. I'll just pop that plot up so it's a little easier to see. So we designed these experiments to try and mimic the largest peaks within each grid cell in these emission files. So this is an area average, so it kind of creates a little bit of a misnomer and kind of overestimates the effect of this peak. We really wanted to remove the effect from any spatial variability. So we had the entire Earth kind of pulse its emissions all at once, and then each grid cell had representative spikes of maximum emissions that it would have seen over that period.
Okay.
So this allowed us to really isolate that temporal variability contribution.
Okay, thanks. We have time for another question if anyone has any. Oh, Adam, go ahead.
Oh, that's one. Kyle, it's very interesting. And just to get to the point you just made, have you considered doing simulations in which you have the same kind of global mean emission variability, but some spatial variability in where the strong sources are?
Yeah, that's an excellent question. We have. We've been a little limited based off our ability to run simulations. But yeah, I think that would be really interesting to see the effect of the spatial variability and starting to tease apart some of our results, particularly from this, temporal and spatially varying effect of simulating the true CMOS emissions. We can see that the spatial variability does have an effect that this is both a temporal and spatial effect that if we're concentrating our emissions in certain spatial regions, that we see a very similar reduction in the total unforcing average over an area.
Yeah. Okay.
Okay, great. All right. Thanks again, Kyle. Okay, so yep, we're right on schedule. It's great. So yep, Manny, do you want to share your screen?
Hi, yeah, sure. I'll do that. Is it good?
Okay. Yeah, it looks good. Maybe just make it full screen.
Yep. Okay.
Okay, great. Yep. So our next speaker is Maddie Medina, who's going to talk about the impacts of North American lakes and wharf for regional climate. So go ahead.
Okay. Hello, everybody. It's nice being here and talking to you. The talk that I'm going to present today is about the impact of major North American lakes in wharf for regional climate applications. So why major lakes? Well, major lakes are, after oceans, glaciers, and seas, the largest reservoirs of water over the surface of the earth. They can also be highly important in terms of affecting their surrounding neighboring regions. And as a matter of fact, lake effect precipitation and temperature modulation by the lakes have been a well-known effect and phenomena in previous studies. So we are looking at 3 different regions in the North American continental area. These are the regions we'll be simulating. From right to left in this figure and from lower latitudes to higher latitudes are the Great Lakes region, and then which we are going to refer to as GL. At mid-latitudes, we've got the lakes Winnipeg and Winnipegosis. These are shallower lakes. We'll call these LU, this region, the LU region. And at higher latitudes, we have the Great Slave and Great Bear Lakes and Lake Athabasca, which are also closer to the pole. And we're going to call these this region the SPLA region. So the GCM models, global climate models, clearly have difficulty in terms of accurately modeling lake processes, but regional climate models, RCMs, have been coupled with different lake models and have been actually successful in doing so. Here we are using the VARF, Weather Research and Forecasting Model, which is a widely used and open source RCM code, as well as the RFI reanalysis, which is one of the most recent and therefore highest resolution reanalysis available. It has many different levels of physical levels that are enhanced in the analysis present. And we use this as we use the RFI reanalysis as the boundary conditions and or initial conditions of our model. Also note that the RFI grid resolution is about 30 kilometers, whereas the domain grid resolution in all the cases we looked at is 12 kilometers. So we talked about the regions that we're going to be looking at. Then the question is what models we will be used. There are different models that can be coupled with WRF. Some of them are old, some of them are a little bit newer, some of them are actually contemporary. So most of these models are columnar models because of the clear limitations of the RCMs in terms of what they can model. You know, so that's how it is. Columnar models, of course, are very simple to moderately simple, but again, that's how these models work and what we can actually afford. So if we look at the different models, there is the default model that comes with WRF, and I believe that this was first introduced into WRF in 2014. In many papers that have studied this model, it has been shown to perform comparatively poorly relative to the other models. There is also the flake model, which is a widely used and therefore very much tested model, but it's an empirical model also, meaning that it does not solve the governing equation, but rather uses empirical formulas. And also, it has been shown in some past studies that it performs well in certain regions. This was done by Gula and Peltier 2012 and Dozier et al. 2014 works. There are also the more recent models, which happen to be mostly physical models. There's a whole family of such models. Here we are using the GLERL-25 model, which was set forth by the Xiao et al. Group in 2016. And both GLERL-25 and the M model are based on the community land model. However, and both of them are physical models. I think that I forgot to mention what physical means. Physical means that they solve the governing equations, which is in most cases is the diffusion equation. But the GLERL-25 model, when compared to the default model, has certain improvements, and those include a better representation of the diffuse solar radiation and the albedo of the surface of the lakes. They include not only water and ice that's defaultly presented in the default model, but also snow, among other things, that makes the model more complicated, more enhanced in terms of what it represents over the surface of the lakes. All right, so moving on, we have over all 6 runs that span 3 different regions, GLU and Bisla, and 2 models, DM and GL25. We're gonna present the results of the flake model in a future work. All of these runs share a common set of physical parameterization that encompass a wide range of physical processes. We also look at a 20-year historic period for this assessment that ranges from 1979 up to 1999, and this is a clearly extensive historic period. Furthermore, we'll use station data that are useful for the verification of the data that we got. And these come in the form of precipitation station data, which only measure precipitation data, and the temperature ones. And these are shown in the left and right figures in here. So moving on to the results, firstly, we find that the default model usually performs worse near the lakes, and that's not shown here, but that is to be expected that the default model performs worse. Well, because the default model was introduced a long time ago, relatively, and it is not enhanced or developed for the phenomena that we are interested in. So moving on, we are going to look at the other models' performance. First is the GL model. We're going to look at the results in terms of the seasonal averages. And we'll plot the results in terms of the bias of the GL25 model over the bias of the default model. And we'll do so for precipitation on the left and for the temperature at the 2 meter on the right. These two figures are those. And the color palettes, you may want to take a look at those. Smaller values that are darker show a worse performance of the GL20, better performance, a better performance of GL25 model because it has lesser extent of bias when compared to the default model. So darker blue is good. But on the other hand, the yellow color that's bright on the other side actually is worse because it has larger biases relative to the GL25 model has relative biases, larger relative biases relative to the default model. So looking at the GL region again, for most of the seasons, we find that the models perform comparably. But when we go to the winter season, closer to the lakes, GL25 performs better than the default model. For the T2 variable, however, the GL25 model performs better closer to the lakes. You see more darker color pointing closer to the lakes in almost all of the year, except maybe less for summer and fall, but that's actually okay because the model doesn't really perform that bad. Moving on to the LU region, the same plots, but this time for the LU region, we see that if the plots, I am not showing the winter and fall plots for the LU region, but spring and summer are shown here for the precipitation. We see that there is a whole range of under and over performances of GL25 when compared to the default model. And for the T2 variable, however, we see that again, closer to the lake model, there's a better performance of the GL25, except for summer, which there is under and over performances for these shallower lakes. So that's not a big deal because these lakes are shallower, and there's a wide range of performances. Next, moving to the Gospla region. For this region, for the seasons not shown for the precipitation, the performance of the GL25 and DM are comparable, but for summer and fall, we see that the GL25 performs better in terms of precipitation, and this is very important because performing better in fall in summer and fall for precipitation is something that's unique to this region. Moving on to the T2, it shows the same behavior of GL25 performing better near the lakes, but unfortunately it's the reverse during the summer. So after looking all of the aforementioned analysis for the neighboring regions in terms of the precipitation and 2 meter temperature, we also looked at the lakes themselves and the ice area fraction. We did this only for Great Lakes area. We clearly didn't do the other regions because of certain reasons. One of them being that we actually didn't have enough time to do that, but that's going to come in the future work. But looking at the performances of the models here on the figures on the right for different lakes, Lake Superior and Michigan shown here. The dark lines showing the observations, and the darker the dark and thick lines, and the thinner lines showing the model performance. We see that the models overpredict the ice amount by quite a little bit, by quite a bit. But we also, if you zoom in on the plots, you see that Blair 25 performs a little better than the default model. So there's also the flake model's performance, which still remains to be seen if that actually performs worse than the GL25 or default model. then it needs to be it could be replaced with actually better models. But if it really performs better, then it could be a viable candidate as a model to be coupled with the WRF model. And these are for the other Great Lakes showing similar trends. So that's my presentation. Thanks for listening in. If you have any question, I'd be glad to answer.
Okay, great. Thank you very much, Minnie. It looks like there's already a question in the chat or a comment. I can read it out from Peter Taylor.
Mm-hmm.
A key impact of lakes on precipitation is related to lake breezes. If your wharf run are at 12-kilometer resolution, they may not represent lake breezes very well. Is that something you've thought about? Or Peter, did you have anything else you wanted to ask?
No, that's fine. That was my question.
Yeah, so.
Well, I think that's a good question, but we really did not look into lake breezes because, we didn't, we just didn't. So I think that's a really excellent question that could be explored, and but we only looked at the other phenomena that we've looked at. So that could be a future work.
Yeah, was I right about the resolution of the WRF model?
Yes, it's 12 kilometers. That's correct.
Are there any other questions? We're at time, but we actually have a sort of a 10-minute hole in our schedule now. So we do have time for questions.
I do have a question.
Sure, go ahead, please. Yeah.
Hi, a very interesting presentation. I was a bit concerned about the configuration of the simulation.
Yeah.
There's not much of a resolution jump between the driving data and the resolution of the original climate model for once, and your grids are very small. Are each subdomain has its own simulation, or you simulated large and extract the region? There were 3 different domains you simulate.
Yes. So first about the first question that you mentioned, that's a good question. But the Era 5 reanalysis itself is very high resolution. And therefore, we did not need to make large refinements on that. We only did a factor of 3, and that by itself is actually, well, I guess quite good. But we also know that looking at the literature, the 10-kilometer threshold is near the gap where the scale-aware schemes and the non-scale-aware ones reach. However, we did have this in mind when designing our experiments. The schemes that we used were designed such that they are scale-aware, so that we address what you're concerned about correctly. And also, you mentioned that the regions are correct. You also correctly mentioned that the regions are small. Well, that was by design, because we were mostly interested at specific phenomena, really specific phenomena, and those are lakes. And for the purpose of looking at the lakes, at these large major lakes, then I think that having the sizes that we chose for the domains should be good enough, or should be okay. Wow. We do see improvements in when we use better representations, and that's sort of in itself, like the GL25, and in itself it's a better. It shows that the lake models are performing better, and well, that's sort of a validation by itself. I'm not sure if I answered your question.
My other point was those domain, small domains. So the original simulation is very constrained. There's not room to develop much the small scales. And when you do the validation of the precipitation, I think that it might be a good idea to perform some internal variability simulation with only the perturbation into the initial condition, because from what I see in your precipitation result, I suspect that those differences are not necessarily from the lake effect itself, but maybe or strongly due to simply the internal variability.
I see. I'm glad that you mentioned that. One thing that I should also mention is that these simulations were performed for a duration of 20 years. And perturbations not only come in the form of spatial perturbations, but you can also see them in terms of long-term runs. If you have a 20-year period and you take the average over that, then you kind of see the variability in that as well. So
wow.
Yes.
Even after 30 years, you can end up only from internal variability have that level of differences in the precipitation fields. Have a 25-year experience in that, and we have there's a lot of literature on that. So
yes, this is an this is we are in a publication that we did do this for the first for a 10-year period, and then we expanded it to a 20-year period. So the trends that we are seeing in our results did not change at all. But just for the sake of our own sanity and check on the results, we are doing the simulations up to a very recent time, not actually the current time, but I think it's 2018. So that's going to be even longer, 30, 40 years, something like that. So yeah, I think that would be good. And we are taking the, I think the presentation time of the person who's after us. So
it's okay.
I am sorry. I apologize.
No, it's good. We have a little bit of extra time now, so it's great.
Okay.
So you got some good discussion after your talk. So yeah, thank you, Manny.
No problem. No problem.
So yeah, there was a 10-minute block here for a short poster talk, but I believe we don't have any more posters, so we just have a couple minutes now. The next talk will start at 10 minutes to the hour, so a couple minutes. Okay, we have about 1 minute till the next talk. So would our next speaker, Xiao, do you want to maybe share your screen and just get set up?
Yep, I will share my screen shortly.
Thank you.
Can you see my screen now? Perfect. So I will just start to present now, or waiting for maybe 1 minute.
Let's just maybe wait for 30 seconds. Just
Sure.
I'll introduce you in a second. Hang on. Yeah. Okay, so yeah, I think we can start. So yep, our next talk in this session is by Xiao Ma, who's going to talk about investigation of climatology of low-level jets over North America in high-resolution WRF simulations.
Oh, okay, yeah. So good afternoon, everybody. This is Xiao Ma, a PhD student from the University of Saskatchewan. Yeah. So today I'm very glad to introduce my work on the investigation of the climatology of low-level jets over the North America in a high-resolution WRF simulation. Here we go. Like for the introduction, as we all know, the low-level jet is always can be distinguished as the very fast-moving air wagon in the boundary layer or even the lower troposphere, and it should be associated with many types of the weather disasters, like the flooding associated with the extreme precipitation, and we should note that it's also relevant with other interdisciplinary fields like the wind energy productions and whatever the air pollution transportation. Actually, over the North America, it is always influenced by the very frequent low-level jet phenomenon. For example, the Great Plain low-level jet and the California coastal low-level jet, which have the significant impacts on the local climate, therefore generating the very accurate climatology of the low-level jet is in this region is very important for us to help to prepare it to analyze whatever those weather systems happen here. But we should be noted that a very high resolution convection permitting model is the robust tool for distinguish the smaller scale low-level jets and help to generate the accurate low-level jet climatology, because the convection permitting models grid can reduce the uncertainties from the convection parameterizations and provide a final description of the surface terrain. So about the methodology of like identifying the low-level jets, in this study, we just used the classic standard from the bonus study previously. So we can just extract the low-level jet from the vertical wind profiles at each grid point of our model output. So first, the height of the low-level jet core should be under the height of 3,000 meters, and the maximum wind of the jet core should be at least 12 meters per second. And we should be noted like the wind shear of the low-level jet should also be very high. So the wind shear between the wind maxima and the first minimum upwards we met, or even the height of the 3,000 meter should also be at least 6 meters per second. And the wind shear underwards is also should be over 6 meters per second. Besides, we also need to classify the low-level jets into two types based on their different performance of the meridional directions. So we can determine the southerly low-level jet if their wind direction of the jet core is between 113 degree and 247 degree. And we can also identify another types of northerly low-level jets if their direction is between the 293 degree to 67 degree. And for the convection permitting model output setup here, like we just utilize the WRF version of 3.4.1, and the horizontal grid spacing resolution is 4 kilometers, which is very fine to represent whatever those convective processes and small scale systems in this region. And there are 51 eta levels in the vertical direction and up to the 50 hectopascals. And it can also represent very fine under the boundary layer, so which is favorable for us to extract the low-level jet information. And the time period of simulation is between 2000 October to 2013 September. And here the simulation is forced by the 6 hour 0.78 era interim realize data, which resolution is about 75 kilometer, and our outputs will just be 3 hourly. And figure 1 is the target domain of our kind of study region, which contains the whole continental US and the northern Mexico and the southern Canada, including like Quebec to the BC province. And about the results, here we will just focus on the seasonal variations of the northerly lower jet in the North America in this page. So on the map, we can see the climate simulation distinguished about mainly two systems, like the California coastal low-level jets and the northerly low-level jet over the Quebec. But we also should be noted that the we can also like distinguish like those scattered hotspots near the Rockies, like the western Quebec to like whatever the eastern region of the Rocky Mountains over the US. And we can see like the Pacific coastal low-level jet is the most active during the summer months, during the summer months, June, July, August, and whatever the Quebec low-level jet and those scattered wind maximum is the strongest during the winter time. As to the southerly low-level jet features in the different regions, there's no doubt that the Great Plains low-level jet is the most significant systems on this map, and it gets the strongest in the summer. And we can see like the region of the frequency is over 15%, can even reach the South Dakota. And whereas the region is only contained within the Texas during the wintertime, and the activity of the Great Plains low-level jet increases dramatically from the wintertime to the spring, which shows a very obvious signals in this region. As to the figure 4, we show the Dyno cycles of the different low-level jets, and figure 4 to figure 7, we just classify the situations into north and southerly low-level jet in summer and winter based on their different performance in those seasons. So for the northerly low-level jet in the winter, we can see the Quebec low-level jet is the most active during the 03 UTC to 12 UTC, whereas the scattered wind maxima can be strongest during 06 UTC to 15 UTC, which means like they may have that consistent active based on their different local time if we just convert the UTC into their real time based on the different time zones. And for the southerly low-level jet during the winter, so the Great Plains low-level jet is not that significant in these cold seasons, but we can still see a very obvious download signals, and it can get the peak during the 06 UTC to 12 UTC. Other than this, it is totally disappeared at about 21 UTC, which is the afternoon for the local time. And in summer seasons for the northerly low-level jet, like the most important system should be the near the coastal low-level jet near the Californias, And it also illustrates the dino variations, which get the strongest at 00 UTC to about 0.6 UTC based on their coverage area. But it still exists dramatically for the whole 24 hours, which is different from other cases. And for the Great Plain low-level jet in summer, yes, the dino signal of it during the summer can give the most significant distributions on the map, especially at 0.6 UTC. We can see the area of the frequency is over 30%, can even reach the North Dakota or the Southern Canada. But at like 18 UTC to 21 UTC, we can see like there's no more low-level jets occurs over these regions, shows like this system's dino cycles is very strong, like it cannot appears during the certain time. And for studying the mechanisms of the low-level jet formation, here we also set up different case studies, selecting the seasons in which the case low-level jet is the most active and analyze their background circulations and the thermodynamic features for their different cross sections. So the up left is the sea level pressure, and the up right is the geopotential height for 800 hectopascal, and this one is the thermal dynamic. This one is the thermodynamic features of the cross section, in which the shaded one is the potential temperature, and the different lines shows the wind speed, which the negative means the northerly wind and the positive means the southerly wind. And this one is the dino cycle of the frequency function as a function of the local time. So for the Great Plain low-level jet, we can see like it is actually located on the west of the very strong sea level high pressure of the Atlantic, and for the geopotential height, it is also controlled by the subtropical high over the Atlantic. And based on their features of the cross sections, we can see there is a very obvious baroclinic features on the background of this low-level jet. And so just based on whatever their dino cycles shows here, we can conclude that it should be determined by the by these baroclinic situations, like in the afternoon, during the afternoon, like the mountain area was heated by the sunshine, so it has the relatively higher temperature, and the temperature is relatively lower in the valley area. So they can provide small scale thermodynamic circulations, which direction is from the valley to the mountain area, and it should be controlled by the Coriolis, in fact, gradually towards to the right, which is to the north. So the southerly wind maxima can be formed normally during the early evening. So it can reach to the peak by the end of the day and gradually decrease after the sunset, after the sunrise. And for the case studies of the two
about 1 more minute. Okay.
Okay. The case study of the two coastal low-level jets. So they are basically controlled by the land-sea contrast temperature differences. So normally during the summer near the California, the sea area is relatively cold, and during the winter, the land area is relatively cooler. So it makes the small scale thermodynamic circulations formed in the coastal regions, which direction from the cold area to the hot to the warm area. So the westerly wind can gradually towards to the south can, based on the effect of the Coriolis force and the northerly lower jet force formed gradually. Yeah, so based on the conclusions, the convection permitting climate simulations can offer the precise and detailed characteristics of the this region's lower jet climatology. And besides whatever the found lower jets, we can also distinguish those scattered wind maxima near the Rockies, which is very small scales, and the high resolution regional climate simulation can also offer the detailed information to help for diagnose the different formation mechanisms of the lower jets in those different regions.
Okay.
Yeah, so this is all
Great.
I want to show
Super.
in this presentation. Thank
Okay.
you.
Great, thank you. So yeah, thanks for the nice talk. Unfortunately, we don't have any time for questions.
Yeah,
there's a nice comment in the chat. Maybe that's something you can discuss afterwards. So thanks. Okay. Okay. So our next. Do you want to maybe stop sharing?
Oh, okay.
Thank you. Great. All right, Rebecca, you can go ahead and share your screen.
Sure.
Okay, so our next speaker in the session is Rebecca Kavanagh, who's going to talk about seasonal forecasting of winter extratropical cyclones in Nova Scotia. Go ahead.
Hi, everyone. Thank you for attending my presentation this afternoon. I am an intern meteorologist at Environment and Climate Change Canada, but the work I'm sharing today was done at Dalhousie during my recent master's degree with Eric Oliver as my supervisor. So my goal today is to explain how I developed a seasonal forecast model of winter storms that affect specifically Halifax, Nova Scotia, and to share those forecast results. So we'll start with a bit of background about the storms I wanted to forecast. Extratropical cyclones, sometimes called nor'easters, or I'll often call them ETCs, are low pressure systems that occur in the mid latitudes and are driven primarily by baroclinic instability. As anyone who lives on the East Coast knows, these storms regularly impact daily life, particularly in the winter, bringing strong winds and heavy precipitation. Currently, these storms are well forecasted with about 2 to 5 day lead times, sometimes a little longer, but forecasting on seasonal timescales is less advanced. Knowing ahead of the winter season whether we should expect lots of storms or not many storms, or if we should expect more, say, heavy snowstorms or more strong wind storms, can help with economic planning, impact mitigation, and disaster preparedness. Because ETCs are a highly variable field, I chose to narrow my focus specifically to the location of Halifax, Nova Scotia. But the idea was to develop this site-specific forecast with a methodology that could be applied at any location. And I'd like to do that in the future. I built the PredictAn dataset based on a dataset of storms that I tracked from the ERA 5 mean sea level pressure reanalysis in collaboration through an algorithm that my supervisor and I put together. So I selected storms that occurred between the November and March months from 1979 to 2019, and all storms that passed within a 750 kilometer radius of the city of Halifax. So that's what I've visualized in the top panel here, all of the storms that were selected from that selection. And then in the bottom panel, I have a time series of all of the storms per season. The impacts of each storm can be very different depending on what type of storm it is. So I separated the data set into 7 subseries based on storm impacts. And those are storms with precipitation, which were further divided into snowstorms, rainstorms, or mixed precipitation storms. We also had no precipitation storms, storms with high wind, and bomb cyclones. So the maps show in gray the full data set, and then in color, I've overlaid just the storms that fall into each specific subseries. Each subseries contains at least 18% of the total storms, so they all have a reasonable contribution. And only time series with a significant slope is the wind time series in the dark blue here. So these are the variables that I wanted to predict. I chose to do so with a multiple linear regression model, or MLR. So having determined what the predictans would be, the next step is to choose predictors for the model. So I started that process by looking at investigating possible predictor fields motivated by 3 important synoptic features that affect ETCs. So first I looked, I wanted to identify baroclinic zones. It's important to kind of see where upper level divergence happens because that supports your surface lows. And then finally looking at some characteristics of the steering flow. I decided to use September mean values, and I got all of these variables that I'm looking at from the ERA 5 reanalysis. And I also investigated gradients of each of those fields. So in total, I have 16 predictor fields, the 8 listed here, and then times 2 for the gradients of each of those fields. But I considered the values at about 5,000 grid points throughout, so evenly spaced at 1 degree apart. And so I have like thousands of possible predictors that I was looking at to start to choose. So in total, that I have about a bit more than 50,000 predictors that I'm looking at, but I only have 40 years of observations. So my problem is my MLR is underdetermined. So to overcome that, I used a combination of stepwise regression and cross-validation. This process involves testing every possible predictor over multiple training and validation periods. And the first time through, I assess which predictor performs the best in a single variable regression. And then after determining that, I go back through and try every possible predictor in combination with that best predictor in a 2 variable linear regression, and then continue adding new variables until the addition of a new variable fails to improve the model. So at that point, we take our best predictor set out, and then we have our MLR. So the selection process ended up choosing between 2 and 4 predictors for each of the 8 type specific models. The predictor locations appear on this map. The marker color indicates the type of storm being predicted, and the shape indicates the predictor variable. The most common predictor that was selected is from the gradient of total precipitable water vapor field. So now getting into some results of my model. For each of the 8 predicand time series, the observed and MLR predicted storms are shown here, the observed in solid line, the predicted in dashed lines. The gray shading shows the 66 and 90% prediction intervals on the model output. The best model ended up being the snowstorm MLR in the lighter blue here, which has both the highest correlation between predicted and observed storm counts and the lowest normalized root mean squared error. So these results indicate that the models have some skill, but they also have considerable uncertainty. So using the direct model outputs, like the exact number output, isn't likely to be the most useful result that we can get out of this. So we decided to combine those single value outputs with the uncertainty that we have out of our model in the framework of a probabilistic forecast. So the framework that I built has 3 components. First, we have the storm activity categories, and we define those based on the mean and standard deviation of the storm type of interest over the past 40 years. And these form the categories that we'll predict. So the forecast will give the probability that the season is going to be below average, average, or above average. Then we calculate the prediction distribution. So the model output is a single value, which would be located at the top of the curve, but we can also calculate the whole probability density function of our prediction. And this gives the probability of any possible number of storms occurring in the season based on the MLR output. Then we can compare the prediction distribution with our storm activity categories to determine the probability of each category based on the area under the curve between our threshold ends. And then finally, we use likelihood categories to convert those numerical probabilities into wording that we can use in a forecast that's disseminated to the public. So this terminology follows IPCC standards. In this example, the result would be the 3 forecast statements of it's very unlikely to be a below average storm season, it's likely to be an average storm season, and it's unlikely to be an above average storm season. To evaluate this methodology, I used it to forecast the storm track activity for the 2019 and 2020 winter storm seasons. And these years weren't used at any point earlier in the training and validation process. So the model doesn't know anything about the storm activity in these 2 years. The most likely track activity category, according to the model, was realized 9 out of 16 times over the 2 years. And then for 2 that I've shown in yellow here, the predictans were inaccurately forecasted based on the probabilistic framework, but the actual value that came out of the MLR was only 1 storm different from what actually happened in the season. It just happened to be that the threshold between our categories lied between those 2 values. And so they ended up falling in a different category, even though they're quite close together. And so that kind of shows us that we did have some skill in that underlying MLR, but there is some room for improvement in the way that we communicate the result in that probabilistic forecast framework. So that's something that I'd like to adjust and try and figure out how we can get the knowledge out of the MLR accounting for the uncertainty that we know exists in there. Finally, to acknowledge the limitations and space for future work. The scope and timeline of the project didn't allow me to do much experimentation with the predictors. I expect that if I was to spatially average those fields, I could get predictors that have more predictive power, especially in the gradient fields. And as noted in the evaluation of the forecasts also, when the expected activity is near a threshold, the model doesn't necessarily communicate that well. And we could consider adapting the framework to communicate those situations more clearly. And then finally, improving the MLR would improve the overall forecast, or we could consider using a different base model with our probabilistic forecast on top of that. Thank you all again for attending. Please feel free to share any questions or comments that you have in the question period, or you can reach out by email. I've included my email on the top right corner there. Thanks.
Great, thank you, Rebecca. It looks like there's a question. Go ahead, Hyland, you can just unmute.
Yeah, it's a very interesting work. I have one question. Looks like you have a lot of possibilities to select the predictors. You mentioned the thousands. So there's a lot of the predictors. They are not independent. So do you just consider this like overfitting, those kind of problem in your selection of the predictors?
So once I selected one predictor, then in every subsequent run through that I was selecting another predictor, then I removed the correlation with the predictor that I've already chosen from the predictors that I was looping through. So I think that would help to remove redundant information.
All right, another question is, did you compare your forecast performance with the CANSIP system, for example, the seasonal system of Canadian seasonal system? How does your...
I didn't actually look into that yet. That definitely is something I should do.
Okay, thank you.
Thanks.
Thanks. We have time for another quick question. Does anyone have any other questions?
I could ask one, Mike.
Great, thanks, Adam. Yeah.
So thanks for your talk, Rebecca. And following on from Hai's question, I'm just wondering about the predictor selection methodology, and if you've looked into some of the other potential approaches like the lasso, which is not parametric and has some advantages.
Yes. Yes. As I was getting towards the end of writing or putting together my master's, one of my committee members recommended maybe taking a look at the lasso, but with the time constraints that I had, I didn't dive into it. But that would be something I'm thinking of looking at working on this a little bit more, even now that I've finished. And that's something to consider for sure. I'm not sure how similar that method is to what I actually got into, but it would be interesting to check into.
I mean, there are some similarities, but some quite important differences too. So I think it could potentially produce distinct results. Yeah.
Interesting. Yeah, thanks.
Okay. All right, great, thank you. Okay, and we're right on schedule. So, yep, our last speaker in this session is Olalekan Balogun. Olalekan, do you want to share your screen? All right, and this talk is on mesoscale wind and temperature changes over peatlands of the Hudson Bay lowlands. Okay, so go ahead.
Thank you very much, Mike. I hope everyone can see my screen and hear me clearly.
Yep. Yeah,
my name is Olalekan Balogun. I'm from Geography Department at Faculty of Environmental and Open Change at University. And I also like to acknowledge my co-authors, Richard Bello and Kaz Iguchi. And today I'll be talking about the mesoscale wind and temperature changes over peatlands of the Hudson Bay lowlands. We looked at both the impact on the surface energy balance as well as the net ecosystem exchange. But today I'm just going to be focusing on the impact of these changes on the surface energy balance. Now, we know how important the Canadian peatlands are. They cover about 12% of Canada's total land area, and they store approximately 150 gigatons of soil carbon. That's a lot. That's about 25%, a quarter of all the peatlands that we have in the world. So this area is very, very important when it comes to climate change and the likelihood of those areas emitting some of those carbon that has been stored over a long period of time. Now, if you look at this map on the left-hand side here, it shows the peatland extent and the amount of peat that is stored. And you can see this area here where you have a very huge amount of peat. And this is the Hudson Bay lowlands, which I focused on for this particular research. It's a very, very important area. And one of the reasons why this is also important, again, they store about 3 gigatons of carbon. And this area is always impacted by this Hudson Bay that we have here. It's the largest inland sea in the world if you account for the Fox Basin to the north and the James Bay Basin on the south part. So this area, usually influences this Hudson Bay lowlands because it's usually it undergoes a complete cryogenic cycle. So it freezes completely during the winter time, and during the summer it melts completely. So usually during the summer, especially around June, July, when there's still sea ice on this Hudson Bay, compared to the land where there's no longer snow. So there's a huge temperature gradient between the land and the sea, and that influences the ecology as well as the climate of this area. And overall, this Hudson Bay is about 6 degrees colder than the average for its latitude. And because of that, again, it has a very huge impact. And that's one of the reasons why over millions of years, or over thousands of years, there's been this huge deposit of peat in this particular area. Now, lots of studies has been done, in the past, looking at this, the winds that blow from the Hudson Bay. So we have the onshore winds blowing from the bay. So we call that the onshore winds. And then the offshore winds are the one originating inland. And there lots of research has looked at the differences between the temperature and the surface energy balance during the onshore and offshore winds. And some predictions have been made in terms of how these winds will change in the future and how that might impact on the peatlands in that particular area. But nobody has actually looked at it, in terms of seeing how those changes would occur. So what we did was to, most of the studies, again, are very limited because they just use maybe 1 year or 2 years of field data, and it's very difficult to tell, about climate change if you just use a very, very short data set. So what we did, because of the limited data that is available in those northern regions, is to use the North American Regional Analysis data set. So we looked at the data from 1979 to 2018, so a 40-year period to see the changes. So we categorized the winds into onshore and offshore winds. So again, the onshore winds are blowing from the bay towards the Hudson Bay lowlands, and the offshore winds are blowing inland towards the Hudson Bay lowlands themselves. So we had the surface energy fluxes, so we have net radiation, we have the sensible heat flux, the latent heat flux, and the ground heat flux, all from the NAR data, and it's about 32 kilometers horizontal resolution, and it's every 3 hours over the entire North America, but obviously we're interested in this region here. So we have about 194 grid points in this particular region that we have selected. So we're interested in investigating the changes in the wind regimes over the Hudson Bay over the last 40 years. We also wanted to examine the trends in temperatures and surface energy balance between the onshore and offshore winds. And finally, we wanted to analyze the spatial heterogeneity in the magnitude and strength of these climatic changes. Again, the region is always very it's always very difficult to set up like long-term measurement in these areas. So most of the data has been limited over the years. So wanted to see how there's differences over space in terms of what is happening in the region. One of the most popular research in this field from the Hudson Bay Lowlands was conducted by Rouse and Bello in 1985, and more recently by Delijakova in 2016. And they predicted that the offshore winds will actually increase because of climate change and as the sea ice is melting. So, after we classify the winds and the surface energy fluxes into onshore and offshore winds, these are some of the results that we have. So this first one here shows the wind frequency from June to September. We focused on this because that's the time when when the advective influence of the Hudson Bay is the most important, because then the sea ice is just beginning to melt and there's a lot of difference in temperature between the sea and the land. So if you look at the frequency here from 1979 to 2018, you can see the dominance of the offshore winds over the years. There's a decline here. As you can see, the onshore winds seem to be catching up with the offshore winds. So this is the frequency over the last 40 years. The second graph here shows the temperatures from 1979 to 2018. And you can see that usually the offshore winds is always the temperature is always higher during the offshore winds compared to the onshore winds, and that's expected because again the winds are blowing from the bay, which are usually covered with ice, especially in June. And then obviously later in the year, you can see the temperature is still the same. This one here shows the daily Hudson Bay Lowlands QH, so that's sensible heat flux. And you can see for the sensible heat flux, you have a much higher sensible heat flux during the onshore winds compared to the offshore winds. And this is expected again because of, again, the onshore winds are usually moist, right, and are much cooler. So when they blow inland, the land is definitely much warmer and the surface is also wet. So there's not much vertical gradient in vapor pressure because both the overlying wind and the surface is moist. But the difference is mostly in terms of the vertical temperature gradient when it comes to the onshore winds. But the reverse is the case during the offshore winds where the land is wet, but the air blowing over, it's relatively drier and warm. So the most important difference when you have the offshore winds is the temperature, the vapor pressure gradient. So you have more QE going into the energy fluxes when it comes to the offshore winds. And that's why you can see right here that the offshore winds have a higher QE compared to the onshore winds. And for the ground heat flux as well, which is very, very important when it comes to the melting of the permafrost and even possible emissions of peat in those two areas. You can see that the QG is much higher during the offshore winds compared to the offshore winds. So these are the important differences that we found. I wanted to see how this might have changed over the last 40 years. So this shows the wind frequency anomalies again for the last 40 years. And you can see a very important, very significant decline in the frequency of the offshore wind. So it has declined by about 6.8% since since 1979, and a corresponding increase in the frequency of onshore winds. Now, this is very, very significant. We're quite surprised because most of all the other studies have suggested that with the melting of the sea ice and the gradient between the land and the sea will reduce, and because of that, you actually have an increase in the frequency of offshore winds. And that would be detrimental to the Hudson Bay Lowlands and the peats, and there'll be much more melting of the permafrost and possible emissions of carbon from the peatland. But we found the contrary, that over the last 40 years, there's actually been an increase in the frequency of onshore winds. And the most important increase is happening in the month of June, where the difference between the onshore and offshore winds has declined by about minus 34.8%, which is very significant. Now you see here that in 1979, this was positive. This difference was positive, showing that the offshore winds were dominant. But by the time we get to 2018, you can see that it has turned negative, which means that the onshore winds have now become more dominant. So we have a shift from offshore dominance to onshore dominance in the month of June. And you can see there's also a decline here, as you can see, but it's not significant here, but it's minus 21.4%. But you can see it's trending towards zero as well in the month of July. So very, very important finding that we saw here. So this shows the temperature and surface energy fluxes. Again, these are the anomalies over the last 40 years. I can see that the offshore winds are increasing. The temperature is increasing much faster than the onshore winds, which should be expected because we can. Most research have found that the land is warming much faster than the sea, and you can see the difference that we have here. This shows the different months. This is June, July, August, and September. And you can see that the difference between the two is even much more significant than the average that we have here. So this is 3.2 and 2.0, so a 1 degree Celsius difference in this month of June between the offshore and onshore winds, and even much higher difference here in the month of July. But you can see a lot of changes happening, particularly in this month of June and July. This year shows the sensible heat flux anomalies over the last 40 years, and you can see that there's much more. The anomalies for the QH is much higher for the onshore winds, which we talked about earlier on again because of that difference in terms of the vertical temperature gradient during the offshore winds compared to the onshore winds. And you can see QE as well, not much difference between these two. And surprisingly, the QG, there's actually a much higher anomaly for the onshore QG compared to the offshore QG, which is very, very important again in terms of the melting of permafrost in that region. Just a further discussion. So again, so that finding was quite surprising. Again, contradicts all the predictions about the changes in the mesoscale wind regimes in the Hudson-Bay lowlands. So we looked much more into the data and just trying to understand exactly what is going on. So we found that this differential warming trends is responsible for this increased frequency of the onshore winds. So the increase in temperature for both the offshore winds and onshore winds obviously is due to global warming and Arctic amplification. But the fact that the offshore winds were increasing much faster than the onshore winds was really the main story here. And that is due to the land to sea surface contrast in surface warming. And we have found that obviously that's due first to the thermal inertia of the land and the sea, the difference in that thermal inertia, but also is also due to the partitioning of energy for the surface energy budget, as well as this elevated atmospheric CO2 concentration. So elevated atmospheric CO2 concentration will increase the stomatal resistance over the land, which would reduce evaporation. And obviously that means more energy will go into the long wave emissions, as well as the sensible heat flux. So we understand that this is what is going on here, that the land is warming much faster than the sea. And because of that, it's increasing these the temperature gradient between the land and the sea as well as the pressure gradient. So this map that you see here, this shows the North American regional analysis air temperature. Unfortunately, it's in Kelvin. So this is the Hudson-Bay and this is the Hudson-Bay lowlands. You can see the difference in the temperature and the temperature gradient between the land and the sea. And this on the right-hand side shows the anomaly over the last 40 years. And you can see this high pressure positive anomalies over the sea and much lower anomalies over the land. And again, so this is what is driving that increased frequency of the onshore winds in this particular area. And the reason why this is the most important in June, so this map specifically is for the month of June. If you look at this next two maps here, you see on this left-hand side, this shows the albedo at the surface. So this is we're using this as a proxy for sea ice cover. Now, again, this area is usually frozen throughout the winter. The melt starts sometime in June, but you can see that even in spite of of global warming, and lots of research have showed that the sea ice is breaking up much earlier and it's freezing much later in the winter. So we would have expected that, in the month of June, we should have a lot more anomalies, but you can see that the anomalies are restricted here to this portion here, the northwestern portion on the northern side, and also the southern part of James Bay. When in the western part, there is no significant changes occurring in terms of sea ice coverage. So that is persisting over the month of June, and that is what is driving that difference between the land, because over the land during that time, there is no snow on the ground, much more warming is taking place compared to this. And that is what is driving that temperature and pressure gradient and increasing the onshore winds in the region. So we also wanted to see how this varied, across different portions of along different areas in the Hudson-Bay lowlands. And you can see that, so this shows the tau, wind frequency anomalies, and you can see that the changes is not occurring uniformly over the area. And because lots of studies, focus on only specific areas of specific sites in the Hudson-Bay lowlands, you can see that, to be, some of the findings might not be representative of everything that's going on. So imagine if you're doing research in the Churchill and Wapost National Park area, there'll be no changes occurring in terms of the wind frequency since the last 40 years, but other areas are actually experiencing lots of changes. And this difference is also due to the spatial pattern of the melt of the sea ice. If you remember the map I showed you earlier, you can see that there was a lot of changes occurring in this area in terms of the sea ice melt compared to all the other areas in the region. And this shows the areas that have the significant increase in the frequency of onshore winds. The next map here shows the changes in QG over the region. I can see here it shows the p-value, and these are the areas that have significant changes. Again, not much happening around the Churchill and Wapausk National Park area. And again, this is very important in terms of how there'll be the active layer will be melted during the summer time, as well as changes in terms of net ecosystem exchange in the region. This quickly just shows the significant changes that is happening and areas out of all the locations that are having changes. So this, for example, shows the month of June, 88 of all the 194 locations have experienced changes in the month of June. You can see that's where you have the most significant changes happening over the region. And for the study month as a whole, we have 92 locations that have experienced changes in the QG over the last 40 years. Just a quick conclusion. So we found that the linkage between the Hudson Bay lowlands and the Hudson Bay itself has always been implied, but it has never been demonstrated to this extent, both temporarily and spatially. The study demonstrates that the changes in the advective role of the Hudson Bay under present and projected climate change are markedly different than was previously thought. Most remarkably, there has been a shift from the dominance of offshore winds to onshore winds in June over the Hudson Bay lowlands. The spatial heterogeneity identified here raises issues for field-based ground validation experiments, which have commonly been located near centers which offer logistical support. Our findings allow for the identification of hotspots where review of management practices may take on heightened importance in terms of permafrost loss and peatland carbon loss. Thank you very much. I'll take your questions.
Great.
Yeah.
Okay, thank you. Yeah, unfortunately, I don't think we have any time for questions now, but maybe if anybody has any questions for you or any of the other speakers, you're welcome to hang around for a few minutes during the break. So yeah, this is the end of part 3 of Atmosphere Ocean Climate Dynamics. We have about a 20-minute break now. We're going to resume for part 4 at 5 minutes to the hour in about 20 minutes. So hope to see you then. Okay. So thanks again to all the speakers. It was great.
Thanks, everyone.
Yeah. Okay. See you in a few minutes.
See you soon, Mike.